Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be learning about combinations and Bernoulli trial experiments. So, what is a Bernoulli trial experiment? Bernoulli trial experiments look something like this. We have some chance experiment E. We have some chance experiment. We're going to perform my chance experiment multiple times. We'll perform it N times, or trials. All right, and we're going to be looking for some interesting event A. And event A, of course, may have one or more outcomes. All right, got some chance experiment E. We're going to perform our chance experiment N times, or N trials, and we're going to look for some event A which may have one or more outcomes. Each trial will be independent of all others. The independence of these trials is going to be very important in the mathematical formalism that we develop a little bit later. We're going to have to use the notion of statistical dependence. All right, so perform my chance experiment N times, look for some event A to occur, assume that each trial of my experiment is independent of all the others, meaning that the outcomes, plural, of any trial are independent of all future and past trials. What happens when we perform an experiment now has no bearing on what has happened in the past or into the future. Then we'll look for probabilities of things of the following sort. We're going to look for probabilities of the following sort. One might be event A occurs exactly K times in N trials. We might look for the probability of event A occurring more than K times in N trials. Etc., etc., etc. So we try to answer questions like event A occurring exactly K times, or more than K times, or less than K times, or more than or equal to, or less than or equal to, those kinds of things. Those kinds of questions are what we're going to be answering. So, in summary, a Bernoulli trial type of experiment is we have some repeated experiment E. We perform my random experiment N times, or N trials. We look for some interesting event A to occur. We assume that each of the trials are independent of all the others. And we try to answer questions determining the probability that event A occurs more than or equal to, or greater than or less than, or greater than or equal to some number of times in N trials. That's what we're going to do. All right. Part of the mathematical formalism for calculating some of these probabilities depends upon an understanding of the notion of combinations. So let's talk about that for a bit. Combinations. Combinations. This is the number of ways a subset of a collection of objects number of ways a subset of a collection of objects can be ordered, or not ordered, can be grouped in unique ways when the order does not matter. All right, so combinations are the number of ways that a subset of a collection of objects can be grouped in unique ways when, and this is very important, the order does not matter. If the order of the groupings matters, we get into a slightly different concept known as permutations. We'll talk about permutations a bit later on in the semester. But for now, what we're looking at are combinations, and the order of the groupings does not matter. All right, this is best demonstrated by example. So imagine we've got a set with 4 elements in it, capital A, B, C, and D. All right, we're going to say here N equals 4 objects. All right, we have 4 objects in my set A, B, C, and D, and we're going to ask the question: how many ways can we group K equals 3 letters in unique ways? When the order doesn't matter. How many ways can we group K equals 3 letters? So K will be the number of elements in the subset. Remember, we're looking at ordering a subset of objects in a collection. K is the number of objects in the subset. And so, very clearly, the answer to this question, just by observation, is that we have 4 different unique groupings, and they are A, B, C, A, B, D, A, C, D, and B, C, D. All right? We have 4 unique groupings when the order doesn't matter. In other words, what I'm saying here is, for example, the group B, C, D, for purposes of determining the number of combinations, B, C, D equals C, D, B, that equals D, B, C, and several other orderings, okay? So for purposes of combination, the order doesn't matter. For purposes of combination, the order does not matter. All right. There's a formula that will allow us to calculate the number of combinations. And it looks like this. Combinations of n things taken k at a time equals n factorial divided by k factorial, also divided by n minus k factorial. So referring back to our original experiment on the previous slide, we have C sub 4, 3. We have 4 letters, 4 objects, n, taken 3 at a time. This equals 4 factorial divided by 3 factorial, also divided by 1 factorial. That's 24 divided by 6 times 1. That's 4. And that's what we saw just by looking at the letter groupings on the previous page. So that works out nicely. Okay, so this is my relationship for calculating the number of combinations, verified by example. A couple of things. The word combinations is also referred to as the binomial coefficients in some textbooks. I almost always will use the word combinations, but if you see the word binomial coefficients, they're talking about exactly the same thing. Another thing, my notation is the combination of n things taken k at a time. That's the way I learned it. It's the way I typically use it. There's another notation that looks like this. Some textbooks will use that notation on the right-hand side of the equal sign, n things taken k at a time in large parentheses. You can commonly find combinations in one of several ways. You can find them in the, typically most textbooks will have an appendix. An appendix where the number of combinations of n things taken k at a time will be tabulated for you. Calculators. Most scientific calculators these days have built-in buttons that you can push to calculate combinations as well as permutations. I believe MATLAB also has a built-in combination calculator. For purposes of tests, I will be making a copy of the tables that are available in the back of your textbook, just in case your calculator battery dies or your calculator doesn't happen to have a combination calculator built-in function. For tests, I will provide you with a table of combinations that you should be familiar with. All right. Back to Bernoulli trial experiments. So to remind you what we're doing, we have a chance experiment E. And we're going to perform it in independent times. All right. We're going to look for some chance experiment A. Excuse me, some event. Look for event A to occur. A may have one or more elements. The probability that event A occurs in any given trial equals little p. The probability that event A does not occur in any given trial is Q, and A either occurs or it does not, So therefore, Q has to equal 1 minus P. So this is the probability that A occurs or does not occur for each trial. All right? And what we're going to do first is we're going to ask the following question. What is the probability that event A occurs exactly K times in N trials? All right, that's the question we're going to answer first. What's the probability that event A occurs exactly K times in N trials? I sometimes refer to this as the central question. And I say that because if we can answer this question, we can answer just about every other question related to Bernoulli trial type experiments. So let me just write down the result and then I'll dissect it on the next page. The probability that in N trials event A occurs K times, all right, let me write this down. This is the probability that event A occurs K times in N trials equals, and again, I'm just going to write this down for now, and I'm going to dissect it slowly on the next page. This is okay. So what we're going to do is we're going to multiply the probability that A occurs K times all right. We're going to multiply that times multiple probabilities that that event A does not occur. So this will occur in minus K times. And we will have to multiply that times the number of combinations of N things taken K at a time. Okay, let's dissect this a bit and talk about what it means. First of all, recall that probability of A intersect B, which is the same as probability of A and B occurring simultaneously, equals the probability of A times the probability of B if A and B are statistically independent. All right? That's why we've got a lot of probabilities of A and or A not multiplied by one another in the relationship on the previous page. The trials are statistically independent. Therefore, we multiply the probabilities of A or A not occurring together. That's the first thing. The next thing to consider is that event A can occur in the first K trials, the last K trials, or anywhere in between. All right. Event A can occur in the first K trials, the last K trials, or anywhere in between. All we want is that A occurs K times out of N trials. All right. Another thing to keep in mind is each sequence of N trials, for which A occurs K times, are equally probable. All right, each sequence of N trials for which A occurs exactly K times are equally probable. And there are C sub N sub K such sequences. All right? All right. So, back to our story. Probability that in N trials, event A occurs K times equals That's what that looks like from 2 slides back. I've got event A occurring K times, K of those, and I've got N minus K of these, and I multiply, so at this point I'm more or less tacitly assuming that event A occurs the first K time, and that event A naught, or A does not occur, the last N minus K times. But that's equally probable to all other sequences of N trials for which A occurs K times. Multiply that times the number of combinations, and I get the overall probability. So let's simplify the notation a bit. Remember, the probability that A occurs is little p, so it'll be p raised to the kth power, q raised to the n minus k power, and then the number of combinations. All right, one more step. I prefer to typically write it this way: p raised to the k power, 1 minus p raised to the n minus k power times the number of combinations of n things taking k at a time. That is the probability that in N trials event A occurs k times. That is what I call the central relationship for Bernoulli trial experiments, and keep in mind that the probability that event A occurs in any given trial is lowercase p. All right, this is our central relationship. It's the probability that event A occurs exactly k times out of n. From there we can do just about everything else. Okay, Let's look at a couple of examples. Let's say we've got a 32-bit digital word. A 32-bit digital word. And I've got a probability of error of 10 to the minus 3. This is for the detection of each bit. In other words, as I'm detecting the individual bits in my digital words, each bit has a chance of 1 in 1,000 of being detected in error. Okay? And what I'm asking myself first is, what is the probability that when I detect 32 bits in a row, that exactly 1 is in error? All right. Well, we can use our relationship from the previous slide, and we find this probability that out of 32 bits, exactly 1 is in error is 1/1000th raised to the first power times 0.999. The probability of not being detected in error raised to the 31st power times number of combinations of 32 things taken one at a time. That's clearly 32 times, 32 ways. 32 ways I can take 32 things and examine them one at a time. And that turns out to be 0.031 or 3.1%. 3.1% likely that exactly 1 bit will be detected in error in any sequence of 32 when the probability of error for detecting each bit is 1/1000th. All right. Let's do another one. What is the probability that out of 32 bits I have exactly 0 errors? This is the probability of no errors. Okay? Well, that's just 0.001 raised to the 0 power. 0.999 raised to the 32nd power, and the combination of 32 things taken 0 at a time. This is 1 times 0.999 to the 32nd power, also times 1. The number of ways you can take 32 things 0 at a time is exactly 1. And this turns out to be 0.9685, or about 97%. It's about 97% likely that in any given 32-bit digital word you will have exactly 0 errors, assuming that the probability of error for any individual bit is 1 in 1,000. All right? Let's do a different example. The repeated experiment will be to toss a coin 4 times. And we'll assume it's a fair coin, meaning that it's 50% likely to land heads and 50% 50% likely to land tails. All right. Question we want to answer is, what is the probability What's the probability of tossing at least 2 heads? All right, what's the probability of tossing at least 2 heads? That's a little bit different than exactly 2 heads. All right, well, the probability of at least 2 heads equals the probability of exactly 2 heads plus the probability of exactly 3 heads plus the probability of exactly 4 heads. All right, the probability of at least 2 heads, is found by adding up the probabilities of exactly 2 heads, exactly 3 heads, and exactly 4 heads. That's how we're going to do it. We use our central relationship to calculate a slightly different result. So this will be the summation of probability of tossing my coin 4 times and getting exactly 2 heads, plus the probability of tossing my coin 4 times and getting exactly 3 heads, plus the probability of tossing my coin 4 times and getting exactly 4 heads. All right. Well, easy enough. Probability tossing it 4 times and getting 2 heads is 0.5 squared, 0.5 squared. It's 50% likely that I'll get heads. It's 50% likely that I'll not get heads. And then times the combination of 4 things taken 2 at a time. This turns out to be 0.25 squared times 6, or 0.375. Probability of 4 things, tossing my coin 4 times and getting exactly 3 heads is 0.5 cubed times 0.5 times combination of 4 things taken 3 at a time. And that is 25%. Probability of getting exactly 4 heads in 4 tosses is that is 0.25 squared times 1, or 0.0625. That's 1/16, of course. All right, add all of those up, and I get 0.6875, or 11/16. All right, this result up here, when it's all said and done, add those up, and I get 11/16. All right. So hopefully that will allow you to understand what I call my general formulations. My general formulations for Bernoulli trials. I've got 4 I'm going to write down. First one is the probability that A occurs at least K times in N trials, that equals the summation I equals K to N probability P sub n of I. All right. This guy right here is my central relationship. Okay. All right. Second one. Probability that event A occurs no more than K times in trials. That is the summation from I equals 0 to K of P sub n of I. Once again, my central relationship. Third one, probability that A occurs more than K times in trials. Equals summation of I from K plus 1 to N of P sub n of I. Once again, my central relationship. And my last one is the probability that A occurs fewer than K times in trials. That is summation of I from 0 to K minus 1 P sub n of I. So, our central relationship allows us to calculate the probability that A occurs exactly K times in N trials. But by using some simple summations, we can calculate the probability that A occurs at least K times in N trials, or no more than K times in N trials, more than K times in N trials, or even fewer than K times in N trials. Should be pretty straightforward from there. All right. That's all I've got for you for today. As always, if you have any questions, please feel free to contact me at your earliest convenience, and I will do my very best to answer all questions. Have a nice day. Bye-bye.